everybody. Today we're going to talk about section 6.2, which talks about the trigonometric form of complex numbers. So let's remind ourselves a little bit about complex numbers. So complex numbers have the form a plus bi, where the a here represents the real part, and the b, again, whatever's in front of the I, is my imaginary part. So this is the form of a complex number. So how would we actually graph a complex number? And it's actually very similar in how we graph points in our Cartesian plane. And so we have our horizontal axis is going to be our real axis here. And the vertical axis is going to be our imaginary axis. All right, and so we would first figure out what our real part is and then figure out what our imaginary part is. So let's try a couple of different examples. So I'm going to call this example A. Let's suppose that we have 3 plus 4i, this complex number 3 plus 4i. This is going to be the same thing as in point notation as 3 comma 4. And so when we're graphing it in the complex plane, all we have to do is, again, my real part is 3, and so we're going to move horizontally, it's going to be 3. And then my imaginary part is 4. And so it's positive, so we're going to move up 4. So that's our first point there, my point A. And so again, we focus on what the real part is, and then we focus on what the imaginary part is. Let's try another one, just to make sure that we got it down. So the other example would be negative 2 minus I. So I'm going to put it in point notation. And so my real part is negative 2, and my imaginary part is negative 1. So when I plot it, again, my real part is negative 2, so it's going to be on the left-hand side, and my imaginary part is negative 1, which is going to be below the real axis. So hopefully you realize that it's very similar to plotting points in a Cartesian plane, except we have a real and imaginary axis in this case. Every complex number is going to have a modulus. And so you might be asking yourself, like, what is a modulus? So let me actually come over here and define it. So let's talk about the modulus. So the absolute value or modulus R of a complex number a plus bi is defined to be R is equal to the absolute value of a plus bi. It's defined to equal to the square root of a squared plus b squared. And so again, it's defined to be the square root of the real part squared plus the imaginary part squared. So a better way to think about the modulus is that R, which is again the modulus, is the distance from the origin to a plus bi. So again, suppose that we have a point here somewhere in the first quadrant, and so my modulus would be the distance from the origin to that point. So that would be my R. Okay. So again, it's also known as the modulus. So why would we need the modulus? And so we're going to talk a little bit about how to actually write a complex number in trigonometric form. And notice that it has the trigonometric form in it, so that means that we're going to have to use some sort of trig functions here. Okay, so again, we're going to be converting a complex number in terms of trig functions. And so we do need to talk a little bit about the modulus. So let's actually start off with talking about a complex number. So I'm just going to call this complex number, I'm going to call this z is equal to a plus bi. That's my complex number. So let's suppose that it's somewhere in the first quadrant. Again, just to make things a little bit easier here. So let's suppose that that is my complex number. And so in point notation, this is going to be A, comma, B. The real part, comma, imaginary part. Right? And so we are trying to write this complex number into trigonometric form. So we're going to have to use our trig functions, which means we're going to have to figure out, we're going to have to use a right triangle here in order for us to, talk about sine and cosine. So we can actually create a right triangle. So by connecting the origin to my point, well, we know that that is equal to r. That is my modulus. So we know that the distance from the origin to this complex number, again, that's our modulus. Well, we know that that's r, or we're defining it to be r. Notice that there is some angle here. So there's an angle from the positive axis, the positive real axis, to whatever my modulus is. We have some angle there, some angle theta. So if we drop this perpendicular line here to create a right triangle. We've done this a couple times in class. So hopefully you guys, hopefully this looks familiar. So let's talk a little bit about the distances here. Okay, in order for us to rewrite a plus bi in trigonometric form, we're going to have to define a in terms of r and in terms of theta, and also b in terms of r and in terms of theta. And so we do know that the distance from the origin, so we know that the base of the triangle, this distance here, is a, and we know that the height of my right triangle is b. And so we know all of the sides, the length of all the sides of this right triangle. And so let's see if we can actually write a in terms of r and theta. Let me ask the question here. What is a in terms of theta? All right, well, here we know that a would be the adjacent side of theta, and we know that r here is our hypotenuse. And so in order for us to use adjacent and hypotenuse, we could use the cosine. And so we have cosine of theta, we know that that's equal to a over r. And so if we multiply both sides by r, we actually get that a is equal to r cosine of theta. And so little a here it's the same thing as r cosine of theta. And when we actually talked about the unit circle, within the unit circle, we know that the radius is r, the radius r is equal to 1. And so we know that the x coordinate is just whatever cosine of that angle is. So it's very similar here as well, except here we don't know what r is. We don't know what the modulus is. It's not always going to be 1. And so we would do r times cosine of theta. Now we found a in terms of r and theta. Now we have to find b in terms of theta as well, and r. What is b in terms of theta? So we know that b here is the length opposite of my theta, and we know that r is my hypotenuse. And so the trig function that we can use here would be sine of theta. That would be b over r. And if we solve for b, we get that b is equal to r sine of theta. And again, just to relate it back to the unit circle, okay, in the unit circle, r was equal to 1, and my x-coordinate was whatever sine of theta was. All right, so now we have a and b in terms of r and in terms of theta. So we could rewrite, z is equal to a plus bi, well, we could rewrite this in terms of r's and thetas, which would be in trigonometric form. So we know that a is equal to r times cosine of theta, and we know that b is equal to r sine of theta I. Well, actually, b is equal to r sine of theta, and then we have our little I there. And so here, notice that both of those terms have an r, and so I'm going to rewrite this. I'm going to factor out an r, so this is going to be rewritten as r times the quantity cosine of theta plus I sine of theta. All right, so in order for us to be able to write a complex number in trigonometric form, all we have to do is find r, or modulus, which is again is the distance from the origin to our point A comma B. All right, and also we have to find our angle theta. And so again, that would be the angle in standard position that contains the point A comma B. So let me write all this down. So we know here that r is equal to the square root of a squared plus b squared. And we also know that theta here is equal to the angle in standard position whose terminal side contains the point AB. And again, the point AB, A is a real part, B is our imaginary part. The best way to find theta is by using tangent, because again, tangent uses opposite over adjacent, and so we would already know B and A. So that would make our lives a little bit easier. But again, you're welcome to just use sine and cosine and take the inverse to find your angle. But again, remember that the angle is in standard position, and so it's not. It's you have to make sure you know in which quadrant that angle lands, and make sure that you're being careful with that. So we could use tangent theta is equal to b over a. And so if we use the inverse here, we would get theta. But again, what I'm trying to say is you have to be very careful, because remember, tangent inverse is going to give you angles between negative pi over 2 and pi over 2. And so depending on where your angle is and what quadrant it is, you're going to have to adjust to that. Okay, so just warning you there. So let me make a note here. So let's make a note. Check the quadrant. So hopefully this gives you a little bit idea of what I'm talking about. Okay, make sure that you are considering which quadrant this angle lands in. So here I wrote down a little summary. All right, so a complex number can be written in trigonometric form as r times the quantity cosine of theta plus I sine of theta, where r is equal to the square root of a squared plus b squared. And again, theta is an angle in standard position whose terminal side contains the point AB. Again, r is called the modulus, which again is the distance from the center, from the origin to the point, and theta here is called the argument. And so again, this angle that's in standard position, we can also refer to it as the argument. So r is our modulus, and theta is considered to be our argument. And again, we don't always have to use theta, but whatever whatever symbol you're using to represent your angle, Remember that that's called your argument. And so if I ask you find the argument, I'm asking for this angle that's in standard position that contains that point. Let's try some examples here. So I have A and B, and so the directions are write each complex number in trigonometric form. So again, we would have to find the modulus and we would have to find the argument. So let's actually start with A. 3 minus 2i. I like to kind of plot it out. Obviously, it's not a very accurate plot, but I do like to know which quadrant this point lands in. And so again, our real part is positive 3, and our imaginary part is negative 2. And so that puts us in the fourth quadrant. So just taking that into account, because when we want to find the argument, we have to take that into consideration. And so we have to find our modulus, which again is the length from the center, from the origin to that point, and we have a formula for that. So we have that r is equal to the square root of my real part squared, which is 3, plus the imaginary part, which is negative 2 squared. So I get r is equal to the square root of 9 plus 4, and r is equal to the square root of 13. And again, we cannot really simplify that. That is the exact value, and so I'm just going to leave r as the square root of 13. And so the distance from the origin to my complex number 3 minus 2i is the square root of 13. Now we have to actually find the angle theta. So I'm gonna just keep it consistent. I'm gonna call this theta as well. So again, we have to find theta. So we know that we can use tangent. So we can use tangent of theta is equal to b over a. I could use that. So we have tangent of theta is equal to, my b in this case would be negative 2 and my a would be 3. And so tangent theta is equal to negative 2 over 3. And so if I use the inverse, so tangent inverse of negative 2 over 3, my theta actually ends up equaling negative 33.69 degrees. But again, notice that angle is actually um, the clockwise angle from the positive real axis to my terminal side. But I'm actually looking for the angle in standard position, and so I am looking for the angle in here in orange. And so we know that one whole rotation is going to be 360 degrees. And so if I do 360 degrees minus 33.69, then I would actually get the angle in standard position. So here I have that theta, the actual theta that I'm looking for, is equal to 360 degrees minus 33.69 degrees, which is approximately 326.31 degrees. And so now we can actually write it in trigonometric form. So we know that 3 minus 2i is the same thing as the square root of 13, parentheses, cosine of my theta, which is 326.31 degrees, plus I, and then sine of that same angle, 326.31 degrees. So that is 3 minus 2i in trigonometric form. So again, this is our summary here. And so I'm going to box this. Oh, to make it easier for you guys to find later. Okay, so that was one example. So let's try B. So B is -2 plus 2i square root of 3. So I like to plot this point or have an idea of where this point lands in which quadrant. Again, that's going to help me with figuring out what the argument is. So my real part is -2, and my imaginary part is 2 square root of 3. So that's going to be somewhere in the second quadrant. So again, this is somewhere in the second quadrant. And so I have to make sure that my argument is an angle in the second quadrant. Right, so let's actually find everything. So we know that R, the modulus, is defined to be the square root of my real part squared plus my imaginary part squared. So here we get R is equal to the square root of -2 squared gives us 4. And here, by rules of exponents, we get 4 times 3 here. And so R is equal to the square root of 4 plus 12, which gives us the square root of 16, which gives us just 4. So we know that the distance between the origin and our complex number -2 plus 2 square root of 3i is just 4. Now we have to find our argument. So we could use, again, tangent of theta is equal to 2 square root of 3 all over -2, which is equal to negative square root of 3. And so again, here you can use tangent inverse, or you can just think about it as, what angle such that tangent of that angle is equal to negative square root of 3 in the second quadrant. And so this is going to be one of those common angles. So here, theta is going to equal to 2 pi over 3. And so tangent again of 2 pi over 3 is equal to negative square root of 3. So again, you don't have to always use the inverse. Okay, if you can tell that this is going to be a common angle, then again, you can just figure that out. And so my argument is 2 pi over 3, and my modulus is 4. And so we could rewrite this in trigonometric form as 4 parentheses cosine of 2 pi over 3 plus I sine of 2 pi over 3. And the way that you can check if you did this correctly is by actually evaluating it. So what is cosine of 2 pi over 3? What is sine of 2 pi over 3? And then distribute that 4 and you should get your previous step. So you can always check your work. So for example, then example 2 is pretty much doing that proving. And so we're going to be given something in trigonometric form, and we're going to go back and write it in complex number form. So write the complex number in the form a plus bi. And so we know that r is the square root of 2, and we also know that the argument is pi over 4. And so we're going to be having a complex number that is in quadrant 1, because again, the argument is pi over 4, which is in quadrant 1. Okay? And so the way to write it back in a plus bi form, which is a complex number, we can just evaluate it. So we have the square root of 2, and we know that cosine of pi over 4 is the square root of 2 over 2. And sine of pi over 4 is also the square root of 2 over 2. So here, we just distribute the square root of 2. And so we have the square root of 2 times the square root of 2 over 2 plus I square root of 2 times the square root of 2 over 2. And again, this is going to give us the square root of 2 times the square root of 2, which just gives us square root of 4, which is just 2, so 2 over 2, plus I, again, square root of 2 times the square root of 2 gives us square root of 4, which is just 2, 2 over 2, and so this trigonometric form comes from the complex number 1 plus I. So 1 plus I is the same thing as the square root of 2 times the quantity cosine pi over 4 plus I sine of pi over 4. So again, you can always go back and forth. So you can always go from trigonometric form to complex number, from complex number to trigonometric form.